Just let me remind you, we discussed the three-phase circuit, okay, before, but for diode situation, when we have diode, which is uncontrolled, now we will have thyristor. We will have control on the starting point of rectification. The same circuit, previous circuit, this is ideal circuit, as you can see here, VA, VB, VC. Rather than D1 35462, it will be T1 3546, but T to me, it means thyristor. And as you know, thyristor 1 and 3 and 5 will conduct the positive part, current will follow here, and the return will be the negative part through either T2, 6, or 4. In the same discussion for diode. And let me remind you with diode circuit, you remember in diode circuit, we discussed this before on the previous week, that we have VAN, VBN, VCN. We look to the highest voltage. Which diode connect to the highest voltage? That diode will conduct the current. As example, here diode D1, okay, here D3, here D5, because they are positive, here again D5 from previous cycle. So see the red color here, red color for VCN until the point here of intersection. We mentioned that after that point, the blue will be the highest voltage, which is VAN, which is connected to diode D1. So this pulse will appear until the green came, it will appear until the red. So from that upper part, positive part, in this way. From the negative part, it will be in this way. The difference between them, VP minus VN, will give me the output voltage, which would look like here 6 pulses, as you can see. We mentioned that in each leg, as example D1 with D4, okay, this leg A, connected to VAN, okay, we can see that each diode will conduct 120 of the time, 1/3. So here you can see here 120, where we have diode D1 conduct, and the negative part 120 diode D4 conduct VAN. This is the same thing for leg B, leg C. This is for diode. It's clear here in this figure. We discussed it before. What about thyristor? Thyristor, the point here of intersection, yes, the voltage VN is positive, but thyristor T1 will wait until alpha came. So from this point of intersection, we will account until alpha came. When alpha came, voltage will appear across the load. Before that, voltage, the same voltage of the previous cycle thyristor will conduct. Now it will continue until this point. Yes, VBN is the highest voltage, the positive forward voltage, but thyristor connected, which is T3, will not conduct until from here to here alpha came, then it will conduct. So if I want to sketch it here, we will see that in this way. You see, alpha, when it came, we account from the point of intersection. Alpha came, the voltage appeared. So this is how the thyristor circuit fill bridge will work. It's the same operation, the same principle, thus we wait until alpha. Now in diode circuit, you remember we derive formula which say 1.35 V line 9, which represent this 6 pulse. Okay, now in this situation, we lose part, this shaded part, because of alpha. So the same ideal, this is VD alpha, the same ideal minus the drop part. It happened every 60 degree. Okay. Now VAC, which means VA minus VC, we did it, we found it in the previous session, okay, to be V line to line square root with maximum sine omega t. This is a phase to phase. Okay. When we integrate for thyristor, when we integrate from 0 to alpha, the part we just lost, okay, we got it here. Integration of sine is minus cosine, just substitute, we got it here. Now, VD alpha now is the same, we found it to be the same 1.35 V line to line, similar to the ideal, to the diode situation, just multiply by cosine alpha. You see? multiplied by cosine alpha. Now here I can control alpha, increase alpha, reduce the voltage here. I got control on this on the output, but I lose part of the voltage. Now this application, this thyristor circuit is useful for many applications in industry. In industry, you know the machine, the ovens I mentioned before. If you have, as example, motor, DC motor, you want to control it. It's part of the process of production, food production, or ammonia or hydrogen production, or some chemical for cleaning, or let me say an aluminium production, or whatever it is. You increase or decrease alpha, increase or decrease the voltage, increase or decrease the speed, it reflects on the production. Okay? So increase the speed or reduce the speed through increasing or reducing the voltage, through increasing or reducing alpha, will reflect on the production. Now this voltage, if I multiply it by the current, as we did in the diode, we have formula for power. Now alpha, as you can see here, when alpha is 0, we say 1.35 cosine alpha. Alpha here going to 0, the whole expression going to 1. Oh, it's give me the diode situation. By the way, V line to line, V line to line. Okay, it's giving me the same formula for diode. Oh, does this mean that if I trigger alpha at 0 degree, I have the same equations for diode? Yes, this is the same equations for diode. As you can see here, the same pulses from the point of intersection to the point of intersection, the same pulses. Okay. Now, if I increase alpha into 30, you see how it look like the waveform? You see, this is the shaded area, the voltage, how it look like the output voltage. 60, see the shaded area. 90, I'm increasing. 120, oh, just a minute. We discussed the inversion mode in the previous session, but for single phase. Is this applied also here for 3-phase? Yes, the voltage could be negative. And this means that if I multiply it by the current, it will be negative power, which means the power returning back from the load to the supply. You see, 150, more negative, 180. Now, for harmonic spectrum, it's clear that the triple harmonics removed, similar to the diode circuits. Yes, it's removed in a 3, but keep in mind that we are dealing with balance system, and you understand what the meaning of balance and unbalance. The same formula applied in diode are applied here for I instantaneous current. The only difference is alpha. You see here, I entered minus alpha for all the expressions, individual harmonics, 5th, 7th, 11th, 13th, and so on. And IS is similar to that of the diode because the same waveform for the current, but the only difference is phase shift. And the same thing for IS. If I integrate it, I will get the same formula for diode. If I divide IS1 over IS, I got the percentage multiplied by the displacement power factor, which is cosine alpha. Alpha is the same phase shift between current and voltage. I got the same formula. Okay, just we have here cosine alpha. Now, what about if I have inductance on the supply? It's not anymore ideal. There is inductance on the supply. Okay, when there is inductance on the supply, what we expect? Tell me what the process will happen here. You tell me. What we call the process when we have inductance on the supply?
Commutation.
Excellent, commutation. Commutation will occur. It means two thyristors at the same time working in the same direction, which means short circuit. So let's assume from previous cycle, T5 and T6 are working in this way. 5 is the positive, T5. This is the load, or let me say supply in this way. And this is T6 going back. This is connected to, just a minute, T5 connected to VC, and T6 connected to VB in this way. Now, at instant of time, T1, which connected to A, will conduct. So VA, T1 will conduct. You see, this is positive, this is negative here. They are connected at the same point. You see, short circuit occurred here. What we have here, just a minute, we have inductance. Oh, short circuit across the inductance, right? Now T1 will work to switch off T5, to switch it off. So T1 will take the positive, T6 will take the negative. If I sketch this here, as you can see, this is T1, this is T5, and this is T6. This is going in this direction, and this is return direction. Just a minute. It's the same circuit we discussed in diode. The only difference here is thyristor rather than diode. But what about the commutation wave? What will happen to the waveform? Have a look. Here at the point of intersection, for thyristor, we say that we need alpha. This is alpha. Now alpha will conduct. Commutation will occur because of the inductance. We have short circuit. We lose another part here, this shaded part. You got it? We lose another part. The only difference here, we don't start it here, we started at alpha, and after alpha we have commutation. While in diode, we started from the intersection. Here at the point here, from here to here is pi over 6, 30 degree. And then we start. After that, commutation occur. While here we need alpha, then commutation occur. So the voltage will be look like this, in this way. I lose two parts. One because alpha, one because commutation. If I apply the same formula discussed before, I got equation for commutation. This is equation for commutation. Now, if alpha 0, if alpha assumed to be 0, what this mean? It's like diode. So if 0 here and 0 here, it means this part will become 1. We got the same equation, the same formula we discussed in in the previous session in last week for diode. The same equation. And the same thing could be, we have also the same formula for the I just derived it in the previous slides for the voltage and displacement wave power factor, as I mentioned in the previous, for single phase, it will be alpha U over 2, as you can see here. Now, it's worth mentioning that many utility, many grids, many companies, electrical companies, many countries, what they do, they make in their standards that limitation for the supply inductance. As example, this is one of the limitations. They mentioned that omega Ls supposed to be greater than this value, which is related to VLL IS1. Okay, it's not open, but because you know what happened is the inductance. Inductance, when we say supply inductance, we are not talking about generator or transformer. Supply is either generator or transformer. Both of them have winding. Both of them have inductance. We cannot make you, let me say, design your input, your supply, regardless the inductance, whatever it will be, because at the end, this inductance will make short circuit. Commutation is short circuit. Short circuit is not a good phenomena unless it's used for application, as example, welding. Otherwise, it is not good phenomena. We are doing short circuit on this affect the supply and the load and the equipment in between. So if I repeat the same discussion, I mean, VL is LDI over DT for the commutation, and I integrate, rather than from 0 to U, I will integrate from alpha to alpha plus U, because this is the thyristor. We don't integrate from 0, from alpha, when alpha came. And I repeat the same discussion here. You see, the supply will apply across the inductance, short circuit, nothing more, nothing less. We have inductance, we have supply, it's applied across it in the short circuit. We did the same formula, we repeated again here, as this is VD. We repeat the same discussion. As you can see, it's the same formula. I copy pasted them here from the diode situation. The only difference, I integrated from alpha to alpha plus U. Why? Because we have thyristor. This is the formula I got, and I will use to calculate U. Okay. Let me also, before I go, for example, do I have example? Yeah, I have example. Let me just mention one more issue before I go to the example. This graph here for individuals, individual harmonics, normalized. It means 5th with respect to phase, 7th with respect to phase, 11th with respect to, and 13th with respect to phase. All of them have the same trend, so I will discuss what I want here in this one. What we can see, increasing commutation, it means increasing the inductance. You can see the individual reduced. So inductance, also one of the benefits of this inductance is reducing harmonics, individual harmonics. Also, increasing alpha, regardless of inductance and commutation, increasing alpha from 0 to 90, also reducing the harmonics. You may say, okay, but I lose the voltage. Yeah, it's compromise. You want to reduce the voltage, you want to reduce harmonics, you increase the alpha, you reduce the voltage. So it's compromise. Now let's take all this discussion in this example. In the three-phase converter shown in figure, previous figure, VLL given to you, frequency given to you. Also supply inductance in microhenry given to you. He asks you to calculate the commutation angle U. He gave you also VD, PD. By the way, sometimes I give you some information indirectly, as example here. Just 1 second. Okay. Now, as you can see here, from this PD and VD, I will find ID. ID is PD over VD, so it gave me ID indirect. The formula I have for voltage is this formula. Now what he did, but don't forget, I need alpha because the formula for U contain alpha. I have ID, I have IL, LS is given in the question, omega is 2 pi F, V line to line is given, so I need alpha to find U. How can I find alpha? I go to the voltage equation here. ID I calculated, LS, omega, V line to line, VD is given in the question. As you can see here, VD is given in the question. I substituted. What is left? Alpha. It's very simple, but you need to take care here while you are working on this type of these numbers, how to multiply, subtract, convert to the other side, and so on. We got alpha. Now I got alpha here, as you can see here. We do the math to find U, as you can see. It's very simple and easy. We got U 3.06. It's worth mentioning that, yes, we use here thyristor, but this is the only control device. Okay, I took it as example because also it's the most used one in industry. And why it's used one in industry? Because when we talk about large, high rating demand, okay, as example, current and voltage in kilo ampere and kilovolt, then we have to use thyristor. But if it is lower than this, we may use MOSFET, field effect transistor, these type. As you can see here, I did it in different type of isolated gate bipolar transistor using pulse width modulation. This is part of my work in my research, PhD research. Here I did it in using Simulink. You can easily do it by Simulink and see how it behaves. And I will stop here. Now, if you have a question, please, I'm waiting to listen to your question.